Okay, so this is our third lecture in our X-ray series, and this is I'm going to sort of mop up the loose ends here, talk about a few concepts, show you how to do some problem solving. So the first thing I want to talk about is this. It's generally desirable for image brightness to be completely uniform, except for when it changes to form an image. And there are a variety of factors that tend to produce variability in the brightness displayed, even when no image detail is present. This variation is random without a pattern, and it can fuck with your ability to interpret images, especially when your desired target is small or has relatively low contrast. So this random variation is what people refer to as noise. Now, one of the factors that decides how bad your noise is how close you are to the detector. Now, when you're close, it's not bad. And when you're far away, it's worse. Just like dose. In fact, exactly like dose, the worseness is described by the inverse square law. Now, I'm going to teach you how to draw this stuff out with regard to how much blur or unsharpness is there, and also magnification. So a long time ago when I was learning this originally, I was trying to memorize, what these different relationships are, and I had a friend who was an engineer at MIT, saw me struggling with this stuff, and was like, "What are you doing trying to memorize that?" And I was like, "Well, that's what doctors do. They memorize things. We just repeat facts out of books. We don't actually know anything." And she's like, "Just draw it. It's way easier to remember it like that, because that's how engineers solve problems. They don't memorize stuff. They understand it, and they draw it out." So once I figured out that, made this a whole lot easier to do. I'm going to pass that knowledge on to you and show you how to draw it. So here's our focal spot. Here is our object. And here is our detector. So if we draw lines sort of like this, this part here that's off to the side, and between those 2 points, that's the so-called geometric unsharpness. So now we're going to move stuff around, and we're going to see how that changes. Before we do that, though, I want to define, get some vocabulary words here. So this is our source to object distance. The red box is the source, and the orange box is the object that we are looking at, the patient. This distance here is the source to detector distance. It's the distance between the patient, or the object that you're imaging, and the detector. So let's do a quick practice problem. What happens to the unsharpness when the source to object distance is increased? So let's draw it out here, and we're going to change it, right? We're going to increase that source to object distance there, like that. Now let's draw it out, see what happens. It gets smaller, right? So that was easy. You don't have to memorize anything. Just draw it out, draw yourself a control, and then draw out what happens when you change it. Now you've got it. So let's do another one. What happens to the unsharpness if the focal spot is made smaller? So now we're going to, again, draw the same thing here. This time we've got a smaller focal spot. Our distance has stayed the same. Drawing it out again. And again, notice that it gets smaller. Now you could do the exact opposite and make the thing bigger, right? And you would see that the opposite relationship exists. So what happens if the object to detector distance is made small? So, make a change right there. Again, draw it out, see what happens. Notice that it's decreasing there also. So another way this can be done is this idea of magnification, which is, this distance here relative to how big the object actually is. So again, we can change some stuff and see what happens. So what happens to the magnification if the source to object distance is made small? So we're shrinking it there a little bit. Draw that out, and we only need one line this time. and notice that there's a slight change. It goes up. All right, so once you've got that, you can figure out all those different kinds of problems just by being able to diagram it out. That concept is much more valuable than like a chart that has the ideas to memorize. Let's move on to a new topic, which is scatter. It's important to sort of understand that scatter does not originate in a straight line. It's not coming from the focal spot. Instead, scatter is a Compton scatter that's occurring from inside the body. So something like this. So like, that kind of stuff. And one of the things you can do, so scatter sort of occurring like this, is that you can collimate it, like with collimators, and that will reduce the amount of scatter. So more collimation, less field, smaller field, less scatter. So that's concept one. Concept two is this. The thicker the body part, the more scatter you're going to have, because you're going to have like more interactions, right? So thin body part, little bit of scatter, thick body part, more scatter. There we go. All right, so and then the last thing, this is something we talked about before, is that it depends on the energy that you're using, right? So above 30, Compton scatter dominates, whereas at low energy you get photoelectric effect dominating. Remember, that's why the photoelectric effect is good. So the probability of the photoelectric effect is inversely proportional to the energy cubed. So here are your three concepts that I think are testable with regard to scatter. So collimation, less scatter, less field, less scatter, thick body part, more scatter, thin body part, less scatter, high energy favors Compton scatter, and then low energies, you have less of it. That's where the photoelectric effect dominates. So let's talk briefly about reducing the scatter, some ways that you can do that. So one of the ways you can do it is by using one of these things, grid, something like that. So turn sideways. And what does a grid do? It blocks X-rays that are not coming into a straight line. So straight ones will go right through, but the ones that are coming in it crazy, not originating, in a straight line, will get blocked and they'll get pushed back out and they won't end up on the X-ray film or detector. So why don't you see grid lines like this? This is a mammogram. We'll zoom in so you can see it. Note the lines here. So why does that happen? That's a type of artifact. Basically, when you've got a Bucky grid, it moves back and forth like this. So during the exposure, which is prolonged when you're using a grid, it's given a chance for X-rays to still have to come in a straight line as it's moving up and down, but it'll overlap in those portions, so you shouldn't see the grid lines. If you do see the grid lines, that means that the grid has failed, so you should not see them. All right. Next thing is understanding that there's this idea of a Bucky factor. Because you're blocking more X-rays because you've got the grid, you need more of them, so you have to increase your MA. And for a particular grid, it depends on the density of the grid, you may need more and more and more MA. So this is what's called the Bucky factor. And a typical Bucky factor is between 2 and 3. There you go. Still blocking them. So yeah. The detector is seeing less energy. It's calling for an increase in dose. MA gets cranked up, and then you get more MA. So what are some pros and cons of the grid? The pro, obviously, is that it reduces scatter, so that improves your contrast, makes an image more diagnostic. The con is that it increases the dose, because you've got to hit them longer and with more MA as a result. And that also increases the exposure time, which gives the patient more time to wiggle, which can potentially lead to another artifact, which is blur. All right, so now let's talk about digital versus analog. So a long time ago, when dinosaurs roamed the earth, radiology was done on film screen. And the differences between this film screen and digital could lead to some multiple choice test questions, so let's go through them. So there are, film screen, what reasons why film screen sucks and some possible advantages. So film screen sucks because it's intolerant to any kind of exposure errors, either under or over, and you can't do the kind of post-processing that you can do with digital imaging. Another thing is noise, which worsens with increasing film size. But lastly is that films degrade over time, whereas a digital image can last for forever, potentially, depending on how it's stored. Possible advantage, it still has very good spatial resolution, and when you hear spatial resolution described, they talk about these line pairs per millimeter, how many distinct line pairs you can see. So what does spatial resolution actually mean? It means that you can distinguish one thing from another that's very close to each other. So I can tell you that those are two separate lines, whereas opposed to something like this, now I've made two lines, but they're so close together that it looks like one line. So this one has better spatial resolution. It's how many line pairs you can see per millimeter. All right, so why is digital superior? Lots of reasons. It has a better dose efficiency, which means you can get away with less radiation, has a wider dynamic range, and it has superior contrast resolution, which allegedly compensates for this mild disadvantage in spatial resolution. So you hear two different types. You'll hear people use CR and DR, so what the hell does that mean? You also hear this terminology indirect and direct, so I'll try to make an attempt to explain that. So let's talk about CR first. So basically you've got this magic substance, these barium fluorohalides, and what they do is they exist in a cassette, and as they're struck by an X-ray, they change states into these metastable stages, which is like a high energy state, and actually hold this for several days. And then you take the cassette downstairs and you scan it with a readout material, and so you put a red light on it, and the parts that are in this metastable state will give off energy as they're reduced down back into some light, and that's readable. And there's a relationship there. The more X-rays that hit it, the brighter the intensity of the light. The CR, like this kind of stuff, can still be used with like a regular portable, basically cassette kind of setup, because you've just got a different instead of having film in the cassette, you've got this magic material. Now, CR has a wide detectable range, better than X-ray, mentioned that once before. You do have to reset it with a bright white light. If you don't do that, you're going to have a ghosting left over. And the spatial resolution depends on multiple factors, but some of them are the laser spot size that you're using, the density of the material inside, and of course the thickness as well. So that's CR. Now let's talk about DR systems, and again we can have direct or indirect. So indirect is sort of the same kind of area as CR, where you're storing your X-ray material in light, and then you are converting that and getting a readout. So something like this. So X-ray hits down in here, light is generated, then you can have a readout here where you've got an electrical change, and then you've got a readout there. So that's an indirect system. Relative to a direct system here, where you're not using any kind of light intermediary, and you're directly creating a charge right there. So let's go back. I want to show the cartoon one more time here. And notice the light. So a couple of things here. Notice that we're using different material, cesium iodine for a light generator versus this amorphous selenium, which is basically just, you're running a charge across it, and that's a direct shot. So watch this. Comes through there. Notice that it comes out like a cone. That's referred to as light dispersion or lateral dispersion of light. That only occurs with this indirect system, and you can imagine that messes up your spatial resolution. So you don't see that with the DR systems. They come straight down. So it's like a straight shot, straight down through there, impacting there. So you don't have that lateral dispersion of light. And that's one of the disadvantages to an indirect DR system relative to a direct DR system. So now let's talk about this vocabulary word called DQE, or detective quantum efficiency. Basically what that means is you have a signal to noise going in and you have signal to noise going out. And in a perfect world, you would have a 1.0 relationship. It would be 1-to-1. All the radiation that is absorbed and made into an image. So the better the DQE, the less radiation you require to make a good image. So when you've got a low spatial resolution, you can have a higher DQE, which makes sense. You need more juice to be able to separate out close things. So for DR, a DQE is around 0.45, and for CR, it's 0.25. In other words, it's better for DR, so you're getting more bang for your buck. Okay, so that's it for this sort of miscellaneous talk, and the next one is going to highlight the differences between mammo and regular X-ray.